Hi guys, it's fair to say I've been dreading making these set of videos, but it's a new spec and I am going to try and tackle the whole of chemistry AQA. I've got no idea how long this is going to take. I'm obviously going to have to go through it as quickly as possible, otherwise we'll all be sat here for like 100 hours. One thing, I'm going to add some timings in the description below so you can try and find out which topic it is you're after, so you don't have to sit and watch the whole thing in case it's just one thing you're after. So, starting from chapter 1 then, chemistry. I've got my notes to help me sort out what I'm going to say, but let's just get going then. What is activation energy? Remember, that's the minimum amount of energy required for a reaction to occur. So why does increasing the temperature increase the rate of reaction? Well, remember the particles have more kinetic energy, they collide more frequently, and they have more successful collisions. Why does increasing concentration increase rate of reaction? Because there are more particles in the same volume, collisions occur more frequently. Why does increasing the surface area increase the rate of reaction? Well, that's because you have more frequent collisions. So do get the term frequency of collisions in your answer, and that will really help. Obviously, if you decrease pressure, concentration, temperature, surface area, the opposite will be true. What is a catalyst? This is asked in both biology and chemistry. A catalyst is a substance which speeds up a reaction without being used up. And in terms of chemistry, you want to say it offers an alternative reaction pathway with lower activation energy. What is a reversible reaction? Where it's where the products can react together again to produce the original reactants. What is the dynamic equilibrium? Now that's the Haber process, and we'll need to talk about that a bit later, but it does just pop up here. Dynamic equilibrium is where both the concentrations of the reactants and products don't change, and that the forward and reverse reactions are taking place at the same time. Marble chips are mainly calcium carbonate. A student investigated the rate of reaction between marble chips and hydrochloric acid. Figure 9 shows the apparatus the student used. So we've got marble chips and hydrochloric acid happily fizzing away in this conical flask, and then a delivery tube taking the gas, which we know must be carbon dioxide due to the marble chips. And also it says it on the diagram, and that's going to be added to the measuring cylinder so we can then work out the volume of carbon dioxide produced. Anyway, I digress. Complete and balance the equation for the reaction between marble chips and hydrochloric acid. Never mix your symbols here. We've symbol and words, we can see straight away that we need symbols because of calcium chloride. So first of all, we've got hydrochloric acid, which is HCl. The formula of marble chips is limestone, so that's CaCO3. And then that produces carbon dioxide and water. You do just need to learn this. And then just have a quick check and see if it's balanced. No, it's not balanced, so we need 2 hydrochloric acids. Have another look and we can see that it's balanced. 9.2, table 4 shows the student's results. I feel a graph coming on. On figure 10, plot these results on the grid, draw a line of best fit. So make sure you're occupying as much of the graph paper as possible. They've told us that time in seconds needs to go along the x-axis. So looking back at the numbers, I've got to plot a 0 here, and then to make sure it all fits, I'm going to go each little square will be 30. Oh, look, I'm running out of space already. Oh my god. And we need to get up to 270. Obviously do it better than that, but you know, iPad. I can't resist adding those bits. Then it's tricky because the volume of gas is so tiny. You kind of need to ignore the little noughts and just look at it as being 30, 46, 52, 65, and that will help you plot. So we need to go from 0 to 0.08, which is the equivalent of kind of 80. So I'm just looking at my axis. So if I go 10, 20, 30, 40, 50, 60, 70, 80, yeah, that fits. And then just when I label the axes, I need to make sure I actually reintroduce those insane numbers of significant figures. So I've plotted all the points. You need to use a nice sharp pencil for this, and now we're going to try and draw a good line of best. Oh, it's too high! Oh, the iPad. Oh, make sure your line goes to your points. So imagine I've shifted that down by ½ centimetre. Now I'm going to have to stay on this page because the next question reads, sketch a line on the grid in figure 10 to show the results you would expect if the experiment was repeated using 20 grams of smaller chips. So smaller chips means a large surface area, which means an increased rate of reaction. And I just need to double check. Yeah, so we're expecting the same volume of gas to be produced, so we need to make sure that the line finishes in the same place. So we're going to see a steeper line, but that it will end in the same place, which is why it'll look like this, and we're labelling it A. 9.4, explain in terms of particles how and why the rate of reaction changes during the reaction of calcium carbonate with hydrochloric acid. So we know right at the beginning the rate of reaction is going to be very high, but then as the reaction continues, the rates of reaction will decrease. The reason being that the acid particles will be used up, which means that their concentration decreases. With decreased concentration, we get less frequent collisions, and therefore the rate of reaction decreases. Another student investigated the rate of reaction by measuring the change in mass. Figure 11 shows the graph plotted from the student's results. Use figure 11 to calculate the mean rate of reaction up to the time the reaction is complete. Give your answer to 3 significant figures. So in order to do this, you need to look at the mass of the mass that was actually lost. So you need to have a look at here where it crosses the line, and then where that line levels out, which is here. So this is quite hard. So you've got 152.5 at the top, and then if you read the bit at the bottom very carefully, you'll see that it's 150.3. So if you take those two numbers away from each other, you get a mass loss of 2.2 grams, and then in order to work out rates of reaction, you need to divide that by the time taken, and that's where you have to look along this axis in order to see where the reaction actually stopped, which was actually at 270, so when it equaled out at the first point. So that's 270 seconds, so then you do 2.2 divided by 270, and that gives you an answer which is 0.00815. Use figure 11 to determine the rate of reaction at 150 seconds. Show you're working on figure 11. Okay, scrolling back up then, so 150 seconds, which is here. We need to work out the tangent. So you're going to use your ruler and draw a nice straight line on top of that. That's horrible, and because it's a rate of reaction, we need to work out the gradient, which is y over x. So m equals y over x. And then you're going to have to read off that x-axis again. So you'll find that this is horribly drawn again, iPad, but you'll find that the mass lost was approximately 0.35, then divided by the time in seconds, which is approximately 50, and that will give you an answer which is 0.07. They do allow a range of answers here because everyone will draw that tangent slightly differently. I just want to quickly talk you through reaction profiles. So you might end up with being given a graph that looks like this, so energy on the y-axis, progress of reaction on the x-axis, and then they could easily give you a level for the reactants, 1 for the products. Incidentally, this is an exothermic reaction because we're going down, which means it's a negative enthalpy change. And then they could show you this sort of thing. And they'd be like, right, label the activation energy. So remember, that's the minimum amount of energy required for a reaction to occur. So you'd have to label from the reactants to the top of that graph line, and you'd label that activation energy. And then another thing they could ask you to do is draw the profile when you've got a catalyst. So because the catalyst lowers the activation energy, you simply need to draw a similar curve, but lower. And that would be the, sorry, it's such a mess. That would be the activation energy with a catalyst. So just be clear that it makes it lower. Hydrocarbon chemistry, this is a massive topic. We're going to be looking at the alkanes, the alkenes, complete and incomplete combustion, but let's dive straight into it with the alkanes. So remember, the general formula of the alkanes is CnH2n plus 2, and you can use that formula in order to work out the molecular formula of any alkane. So for example, what is the molecular formula of the third alkane? Subbing in 3 to that equation gives you an answer of C3H8. You must be able to name the first 4 alkanes, and you want to use monkeys eat peanut butter in order to help you with this. So methane, monkeys, eat, ethane, peanut, propane, butter, butane. So methane, ethane, propane, butane. What is the formula of butane? C4H10. Now remember, alkanes and alkenes are both hydrocarbons, so you need to provide a perfect definition of a hydrocarbon, which is that it is a compound containing hydrogen and carbon atoms only. If you don't say only, you don't get the second mark. Well, someone's much happier now with her head buried in her fur. With the alkenes now, what is the general formula of the alkenes? It's CnH2n. List the first 4 alkenes, Well, remember with an alkene they're very special because they have a C double bond C, which means methane doesn't exist because you need a minimum of 2 carbon atoms to have an alkene. So therefore technically the first alkene is ethene, followed by propene, butene, pentene. What is the formula propene C3H6? You must be able to draw all the displayed formula. Now key terms you need to know is the difference between saturated and unsaturated. We say that alkanes are saturated because all the carbon bonds are single, whereas alkenes are unsaturated because they contain a double carbon bond. How do we actually get hold of the alkenes and the alkanes? Well, we get them from crude oil, and fractional distillation has to occur in order to separate that crude oil into all the different length hydrocarbons. So if they ask you a 4 marker on how to carry out fractional distillation, you're going to say that you heat the hydrocarbons until they evaporate, they rise, cool and condense, and because there's a temperature gradient within that fractionating tower, you find that the short chains condense at the top where it is coolest, the long chains condense at the bottom where it is hottest. You need to know the order of fractions in the fractionating tower starting from the top. So those are refinery gases, remember that they're used in central heating, followed by petroleum, which is used as petrol in cars or fuel in cars. Then you have kerosene, which is airplane fuel, diesel, used in lorries and buses, fuel oil, which is used as ship fuel, and lastly bitumen, which is used for road surfacing. Other words you'll need to know are things like viscosity. Remember that's how runny a substance is. So the more thick a substance is, the more viscous it is. Volatility, that's how easily something turns into a gas. So if they ask you for a comparison of the volatility, viscosity and colour of bitumen and petrol, you'd say that bitumen has a darker colour, it is more viscous and it is less volatile than petrol. Now why are we bothering with all this? Well, it's obvious because we're trying to get fuel that can be burnt to supply our cars, etc. with energy so they can run. So what is a fuel? Well, it's a substance which releases energy when burnt. Now, depending on how much oxygen is available will dictate if you've got complete or incomplete combustion. So with complete combustion, you have a plentiful supply of oxygen, which means the byproducts produced are carbon dioxide and water. Whereas with an incomplete combustion, you have insufficient oxygen and carbon monoxide and water are produced instead. What's the issue with carbon monoxide? Well, first of all, it's poisonous, and what that means is how it actually works is that it combines irreversibly with the hemoglobin in your red blood cells and therefore prevents oxygen being transported. Obviously, there are still issues with carbon dioxide. Carbon dioxide is a greenhouse gas leading to global warming, sea levels rise, etc. So neither of these situations is ideal. There are other pollutants that you get from burning these hydrocarbons. In car engines, for example, the high temperatures found will cause the nitrogen and the oxygen to react. And what happens is nitrogen oxides are formed, they dissolve in water, and that can fall as nitric acid, which is acid rain. Again, you'll get acid rain from sulfur, and this time sulfur impurities in the original crude oil cause sulfur dioxide to be produced. That falls as acid rain. What are the issues relating to acid rain? Well, first of all, it damages limestone buildings. We must say limestone. Secondly, it makes lakes and rivers too acidic. And lastly, it damages trees. They often like to ask you how you test for a saturated or unsaturated hydrocarbon. So what you're going to do here is add bromine water, and with an unsaturated hydrocarbon, you'll see orange colour turning to colourless, and that's because the bromine's added itself to the original hydrocarbon, so it doesn't exist anymore. And here's the equation showing that. With saturated hydrocarbons, you won't see any reaction. Getting more technical again, so what is a homologous series? Remember, it's a family of compounds with the same functional group. So something like the alkenes, they all have a C double bond C. The alcohols will all have an OH group. This question is about organic compounds. Hydrocarbons can be cracked to produce smaller molecules. The equation shows the reaction for the hydrocarbon C18H38. So we can see C18H38 being broken down into lots of shorter hydrocarbons. Which product of the reaction shown is an alkane? So remember, alkanes obey this general formula, which is CnH2n plus 2. So either those things do have to obey it. So the way we do that is we can check them out by doing C6H14. So that would be C6 and then H, and let's make sure, so we would do 2 times 6 is 12 plus 2 is 14. Yeah, it obeys the formula, which is why D or option 4 is the answer, and obviously you would go through and check the others just to show you this one doesn't work, because 2 times 4 is 8, and if you add 2 you get 10, but that formula isn't C4H10, it's just C4H8, which is why it's not an alkane. Table 1 shows the boiling point flammability and viscosity of C18H38 compared with the other hydrocarbons shown in the equation. Which letter A, B, C or D shows the properties of C18H38, how they compare with the properties of the shorter hydrocarbons. So first of all, boiling point is obviously the temperature at which it boils, so the larger the molecule, the higher the boiling point. C18H38 is the largest molecule mentioned, which is why its boiling point must be the highest. In terms of flammability, that's how readily it sets alight. The larger the molecule, the less flammable it will be, so we're looking for lowest on flammability. Finally, viscosity is how readily the substance flows. So the more viscous a substance is, the thicker it is and the less readily it flows. So obviously larger molecules will flow less readily and therefore they'll be more viscous. So you're looking for boiling point highest, flammability lowest, viscosity highest, which is why the answer here is A. The hydrocarbon C4H8 was burnt in air, incomplete combustion occurred. Which equation correctly represents the incomplete combustion reaction? Incomplete combustion requires you to know that carbon monoxide and water are produced, so that brings down your options to A and B, and actually no, we're just looking for water, not hydrogen, which is why the answer here is B. A small cylinder of butane C4H10 contains 5 kilograms of butane. Write a balanced symbol equation for the complete combustion and what would the maximum mass of CO2 that would be released. So let's start with our balanced symbol equation. So we've got C4H10 and we know we're burning it in oxygen, it's combustion, so we're going to add O2. Because it's complete combustion, we're going to make carbon dioxide and water as our products, and then it's a matter of balancing it. So we've got 4 carbons on the left hand side, so I'm going to write a 4 here. And then I'm just going to add up how many, oh yeah, there's 10 hydrogens on the left hand side, so we need to put a 5 here, and then we need to work out how many oxygens there are on the right hand side. So we've got 4 times 2, which is 8, plus 5, which is 13, so we need 13 divided by 2, why am I doing it on my calculator, which is 6.5 oxygens over here. You might want to make it all integers, so that's whole numbers, so you could double it, so it would become 2C4H10 plus 13O2 forms 8CO2 plus 10H2O. Now in terms of working out the mass, I'm going to do it the way I've always done it, so we're going to turn it into a table. By the way, I redrew it so that we've got whole numbers because it will make it easier. So we write mass mR moles as the table. We look at the question, we're looking for the mass of CO2, so we're going to put an X under CO2. We know the mass of butane, it's 5 kilograms, but I'm going to convert that to grams, so that becomes 5,000. Then it's a matter of working out the mR of butane, so carbon has a mass of 12, you get that from the periodic table. We're going to do 12 times 4 plus 10 times 1, because we've got 10 hydrogens and 1 is the mass of hydrogen. Add that up and you get an answer which is 58. Let's work out the mR of carbon dioxide. So carbon is 12, oxygen is 16. We need to multiply that by 2 because of the fact that it's CO2, so it becomes 44. Then we're going to use this triangle, which is mass is number of moles times mR to work out the number of moles. We can see that that's therefore mass divided by mR. So to work out the moles of butane, we're going to do 5,000 divided by 58, which gives us 86.2068. So we want to keep that number nice and unrounded so we don't introduce rounding errors. Then it's a matter of comparing the mole ratio here. So it's 2 to 8. So we've got 4 times as much carbon dioxide. So we effectively take this number and times it by 4, which gives us a value of 344.827586, blah, blah, blah. And then we're finally after X, so we're going to use our formula triangle again. We're looking for mass, so therefore it's number of moles times mR. So we're going to do 344.827 times 44, which gives us a value which is 15,172 grams. So now we're turning our attention to carboxylic acids, alcohols and esters. Looking at the functional groups then, alcohols have a functional group of OH, esters have a functional group of COO, and carboxylic acids have a functional group of COOH. So let's name the first set of alcohols using monkeys eat peanut butter again. So you've got methanol, ethanol, propanol, butanol. And now the carboxylic acids, you've got methanoic acid, ethanoic acid, propanoic acid, butanoic acid. I should probably talk about how esters are formed now. So remember, an ester is formed from a carboxylic acid and an alcohol. And remember, the reaction conditions needed are a strong acid catalyst such as sulfuric acid. The second thing to remember is that it's a reversible reaction. Remember, these reactions aren't ideal because you don't get 100% yield. Now let's work out how we're going to name the ester formed. So we'll take something like methanol, so there's an alcohol, and we're going to add it to ethanoic acid, which is a carboxylic acid. Now the way you work out what the ester is called is you get the first part of its name from the alcohol. So in this case, methanol would become methyl. And the second part comes from the carboxylic acid, so ethanoic acid. So the answer here is methyl ethanoate plus water. So not as difficult as it originally sounds. Give some uses of esters. Well, remember, they're very volatile, so they make great perfumes and flavourings. Uses of alcohol, that's more straightforward. Obviously we use it in alcoholic drinks, but we can also burn alcohol, so it makes a good fuel. Bizarrely, you need to know the equation for when ethanol reacts with sodium. So ethanol plus sodium forms sodium ethoxide plus hydrogen. And similarly, you need to know an oxidation equation for when alcohol is oxidized. So you're going to say ethanol plus oxygen forms ethanoic acid plus water. And that's why when you leave a bottle of wine out after several months, if you actually left it there, you'd smell that it smells like vinegar, because it's actually the same acid. It would be found in both. Now we're moving on to the polymerization topic. So first of all, define a polymer. Well, poly meaning many, so it's actually a large molecule formed from many small monomers joining together. Therefore, what is a monomer? It's a small molecule which joins together to form a polymer. There are several different types of polymerization. One of these is condensation polymerization. In this situation, the only thing you need to remember is that a small molecule is lost when the two reactants come together, and that can quite often be water. What is the general equation for the formation of polyester? Well, that will be a diol plus dicarboxylic acid, and that forms a polyester plus water. I'm going to show you how to draw alcohols. So we know the first alcohol is methanol, the second one is ethanol, the third one is propanol, and because they're alcohols, it means they have a functional group which is OH. Methanol has 1 carbon, ethanol has 2, propanol has 3. And now we're going to add OH because that's the functional group of an alcohol. And then it's a matter of filling in the rest of the H's, because remember, each carbon atom forms 4 bonds, each hydrogen atom forms 1 bond, and each oxygen atom forms 2 bonds. So just double check that everything you've drawn there is accurate. Now I'm finishing off the ethanol. So that looks like that. And then lastly, propanol. And then fill in all the hydrogens, make sure you count all your bonds, and then it shouldn't be too much of a problem. With carboxylic acids, you're looking at names such as methanoic acid. Ethanoic acid means 2 carbons. I am totally illegible doing this. And the third one is propanoic acid. The functional group of carboxylic acids is COOH. So let's have a look at what that looks like. Methanoic acid we know is 1 carbon. Ethanoic acid is 2. Propanoic acid is 3. The functional group is OOOH, so we draw that like this. There's the O, there's the OH. Count your bonds. Carbon has 1, 2, 3, so we just need 1 final H in order to complete methanoic acid. Do the same with ethanoic acid. There's the functional group. And then just add the rest of your hydrogens to complete your compound. Propanoic acid, there's the functional group. Just adding all those hydrogens again. Just going to show you how to draw esters. So in order to create an ester, we need an alcohol and we need a carboxylic acid. So I'm going to pick ethanol as my alcohol. I'm going to add it to methanoic acid, which is the carboxylic acid. It's a reversible reaction, which is why we need that, and it's in the presence of an acid catalyst. The name of the ester comes from, first of all, the start of the alcohol, which is ethanol, which is why it's ethyl, And then the second bit of the name of the ester comes from the carboxylic acid. It's methanoic acid, which is why it's methyl methanoate. And then water is our byproduct. In terms of drawing it, we've got ethanol, so that's 2 carbons. We've got alcohol as a functional group. And then we just need to complete the structure. Methanoic acid only has 1 carbon because it's methyl. We've got our functional group here, and then just complete the structure and then literally stick it together. It's a condensation reaction, which means you lose a small molecule, and that's going to be water. So let's now draw ethyl methanoate. So effectively just stick them together, and this will be your final answer. I swear I'm the world's messiest writer. And then add water because we want to complete it. Let's quickly chat about addition polymerization. So what you'll be taking is an alkene, so that's a C double bond C. So for example, ethene, which is C2H4. And addition polymerization means you're adding lots of ethenes together. So that's our original monomer, which is obviously the small subunit. And then we're going to join it together. So the way you do that is you have to draw some square brackets, break that double bond, elongate those bonds outside of the brackets. Make sure you draw this incredibly carefully. And that's your final answer. So that would be your polymer. Your monomer was called ethene. This would therefore be polyethene. Ethene is used to produce polyethene. Draw the bonds to complete the displayed formula of ethene and polyethene in the equation. Okay, this is a nice question because I've done half of it for you. So we have ethene first of all. Remember, ethene is an alkene, so we need a double bond. And just make sure you count your bonds. So each carbon should have 4 bonds, which it does. 1, 2, 3, 4. And each hydrogen should have 1 bond. And then as soon as it forms polyethene, we know that that double bond breaks, so it becomes a single bond. We elongate the bonds outside of the brackets, and then we just complete as before. Polyesters are made by a different method of polymerization. The equation for the reaction to produce a polyester can be represented as this nasty looking thing here. However, notice that rather than adding loads of ethenes together, you've actually got a variety of what's called monomers. So you've got this one here, and then you've got this one here. And in addition, you've actually got a product which is water, whereas there was no extra product in the equation above. You literally had ethene being made into polyethene, whereas we've got 2 separate reactants and we've kind of got 2 separate products. Compare the polymerization reaction used to produce polyethene with the polymerization reaction used to produce polyester. So like I said, first of all, you're going to say that polyethene was produced from 1 monomer, whereas polyester was produced from 2 different monomers. Then you can say that polyethene is the only formed product in the equation above, whereas polyester also produced water. And then you can actually name the type of polymerization involved. So the equation above was addition polymerization because you're literally just adding ethene monomers together to form polyethene, whereas in this equation we've got condensation polymerization, and that's due to the production of water. Now this next bit's quite tricky. They want you to be able to show how 2 amino acids may form a peptide bond. So I'm going to bring up an example now, because that's the easiest way of describing it. Don't sweat it too much, guys. If you know everything else but you don't know this, you'll still be able to get your grade 9. So don't worry too much. But do be aware that we've lost a water molecule. It's a condensation reaction, and keep an eye out where the bond is formed. And it's formed between the carbon and the nitrogen, and that's forming a peptide bond. Then the syllabus dips into DNA. So remember that DNA is a double helix. It's found inside our cells, and it's responsible for our features, for the proteins which we make. Now, in terms of the structure of that double helix, remember it's made up of a sugar, phosphate and base, and that base can be one of 4 things. It can be A, T, C or G. Remember that A bonds to T and C bonds to G, so the straight letters bond together and the curly letters bond together. These are called nucleotides, so a nucleotide exactly is a sugar, phosphate and a base. Now we're moving on to chemical analysis. So we're going to start with defining a pure substance. So that's a substance made up of only one type of thing. So that could be all the same element, or it could be all the same compound, but nothing else can be mixed in there. I want you to know the definition of a fixed point. So that is the boiling or melting point of a specific element or compound. Now we need to define formulation. So remember that is a useful mixture made up of set proportions. I really hate this topic. It's so random. Like the next question, what is paint made out of? I don't know, who cares? Is that even chemistry? But it's actually made out of a pigment, which is actually the colour of the paint. It's made up of a binder that helps the paint stick to an object. And lastly, it's made up of a solvent, which enables the binder and the paint to mix properly. Another fascinating thing you need to know is what is washing up liquid made out of? And I'm just summarising this as quickly as possible. So obviously there'll be water in there. There's fragrance because you're washing up liquid, smells of lemon or cherries or whatever. It contains rinse agent and also surfactant, which actually helps break down those fat molecules that stick to your pans if you fried an egg or something. And lastly, colouring, because something like very liquid is often very bright green and that's not a very natural colour. What is this about? Now we're going to talk about chromatography. So remember, chromatography is used to separate different inks or dyes or food colourings. You do need to know a little bit how it's set up. So remember, what you do is you get a piece of filter paper or blotting paper, use a pencil line to draw a reference point, then you dot your inks along that reference point, and then you dip the very end into water, and as the water soaks up, it will draw the dyes up and they'll separate and you can see what's in there. Now, why is it drawn in pencil, that reference line? Because obviously if it was drawn in ink, that would rise too and totally screw up your findings. They like you to calculate the RF value, so that's quite a simple equation. You just need to do RF equals distance moved by dye divided by distance moved by solvent, and in this case it would be water. So you'd use your ruler to measure those lines and then you'd pop it into the equation. 7. A student investigated food dyes using paper chromatography. This is the method used. Put a spot of food colouring X on the start line, put spots of 4 separate dyes A, B, C, D on the start line, place the bottom of the paper in water and leave it for several minutes. Figure 5 shows the apparatus the student used. So this is paper chromatography. It's used to separate coloured inks, dyes, food colourings, etc. And if you remember, the water soaks up the blotting paper, dragging the ink with it, and we can work out lots of things from the results. Write down 2 mistakes the student made in setting up the experiment and explain what problems one of the mistakes would cause. Okay, the thing that's really jumping out at me first of all is that they say that the start line is drawn in ink. No, big no. That has to be drawn in pencil. The reason being that when the water soaks up, it would cause the ink line to spread as well. So imagine the mess that would make. So the start line needs to be drawn in pencil. The second thing is the water really only should be touching the very bottom of the paper. It's blotting paper, it's filter paper, so that water will move anyway. The moment you dip it straight in the water, it means that the spreading of inks will occur far too quickly, and then you again wouldn't be able to see the results. Another student set up the apparatus correctly. Figure 6 shows the student's results. The result for dye D is not shown. Calculate the RF value of dye A. Give your answer to 2 significant figures. So first of all, it's important that you know the equation for the RF value. So remember, RF equals distance moved by ink divided by distance moved by solvent or water. So in that case, you need to do, for the distance moved by ink, get your ruler and literally measure this exact distance here. And then for the distance moved by the water or the solvent, get your ruler and measure this line here, which will give you 2 numbers. And those numbers are 2.8 for the distance moved by ink A, 8.2 for the distance moved by the solvent. Pop those into your calculator and you'll get a value which is 0.34 to 2 sig fig. Do make sure you follow the instructions given. Dye D has an RF value of 0.80. Calculate distance that dye D moved on the chromatography paper. This is a reverse calculation. So if we say RF equals distance moved by ink over distance moved by solvent, so we know the RF value we've been given is 0.8. We're looking for the distance that D moved, so that will be X, and we're going to divide it by the distance moved by the solvent, which we just measured, which is 8.2. And then in order to work out what X is, you need to times everything by 8.2, and that will give you a value which is 6.6. Explain how the different dyes in X are separated by paper chromatography. 4 marks, so 4 separate points. You want to talk about the fact that the solvent moves through the paper for the first mark. Then state that different dyes have different solubilities in the solvent for the second mark. Therefore, they have different attractions to the paper for the third mark, and then they're carried to different distances for the 4th mark. So that's really a step-by-step guide as to how paper chromatography actually works. Next up, we're talking about tests. So we're looking at tests for positive and negative ions and more generic tests. So we'll start with the generic test for gases. I think I've already mentioned that the test for hydrogen is that a lighted splint pops. Now do use the exact wording that I'm using because I'm using the most concise, succinct wording possible to make sure you have to learn as little as possible. So to that end, we're going to look at how oxygen is tested for. So this time you want a glowing splint, so one that you've blown out and is now you kind of blown out, but it's still smoking and glowing at the end. And that's going to relight in the presence of oxygen. Carbon dioxide, you're going to bubble that through lime water, and if it's carbon dioxide, it will turn that lime water cloudy. The test for chlorine gas is that it bleaches damp litmus paper. Now we're going to look at flame tests. Remember, flame tests are used to test for positive ions. So you need a clean nichrome wire, which you're going to hold in a Bunsen just to make sure it's perfectly clean. You're going to dip it in your sample of your positive ion that you don't know what it is. You're going to hold it in a roaring blue flame of a Bunsen. That is essential, and you're going to look at the colours formed. If you have potassium, you'll see a lilac flame. If you have sodium, you'll see a yellow flame. Lithium, crimson, it's a very specific shade of red, crimson. Calcium, you'll see brick red. Another way you can test for positive ions is using precipitation reactions, and you're going to add sodium hydroxide as your reagent. Now if you have an aluminium ion, magnesium ion or calcium ion, you'll see a white precipitate formed. If you add excess sodium hydroxide, that white precipitate will dissolve in the presence of aluminium, so you know that that particular ion was aluminium. You get a lovely colour if you add it to copper this time, so ignoring everything we just said. This time you'll get a blue precipitate. With iron 2 you'll get a green precipitate, and with iron 3 you'll get a brown precipitate. Now we're going to look at detecting negative ions, so we're going to start with the halogens, group 7, which we call the halides. So this time you're going to add nitric acid in order to remove any carbonate ions which might interfere with your test. Then you add silver nitrate, and then you'll get the following colour changes. With chlorine, chloride ions, you'll get a white precipitate. Bromine, you'll get a cream precipitate, and iodine, you'll get a yellow precipitate, and it gets darker the lower down in the group you get. And what are those things called? Well, they're called silver chloride, silver bromide, silver iodide. Testing sulfates now, you're going to add hydrochloric acid followed by barium chloride, and if you have sulfates present, it will be barium sulfate and you will see a white precipitate. Lastly, carbonates. This is nice and straightforward. So something like calcium carbonate, add any acid to it, something like nitric acid would work well. It will start to fizz, capture some of that gas, test it with lime water, and because it's a carbonate, you expect that gas to be carbon dioxide. So if it turns milky or cloudy, yes, the original substance you had was a carbonate. 7.5, flame emission spectroscopy can be used to analyse metal ions in solution. Figure 7 gives the flame emission spectra of 5 metal ions and of a mixture of 2 metal ions. Use the spectra to identify the 2 metal ions in the mixture. Okay, it's literally, you have to look at the bottom bar and have a look and see where the lines match up. This is quite a tricky exercise, but you'll see that the calcium lines, if you look down, match up, and also the sodium ions match up. So that's your answer there. Explain why flame tests could not be used to identify the 2 metal ions in the mixture. So let's think about the colours that those flames would go for sodium and calcium. Remember, calcium would go a brick red colour, sodium would go a yellowy orange colour. These colours are very, very similar. So first of all, state the colours, say that they're very similar, that they would mix, and therefore you wouldn't be able to work out the individual colours because you just end up with a kind of blur. Tiny bit now on the Earth's early atmosphere and how it's changed to become the atmosphere of today. So obviously the plants photosynthesized, which means they took in carbon dioxide and then released oxygen, so O2 levels rose, CO2 levels decreased because carbon dioxide got locked up in sedimentary rocks and also inside the ocean itself. You saw the oceans and seas actually form due to water vapor condensing. Remember, the continents came together to form a large supercontinent called Pangaea, and the volcanoes became smaller, and that's due to the formation of the Earth's crust. Let's talk about the atmosphere of today in terms of the relative amounts of different gases. Remember, we have approximately 80% nitrogen, approximately 20% oxygen, and there's a tiny percentage made up of carbon dioxide, water vapor, and noble gases. We've already talked about the crude oil topic, but now we're going to talk about how those fossil fuels originally formed. So they formed over millions of years from the bodies of dead sea creatures, which got crushed under intense pressure and heat, causing layers to come together, and before you know it, fossil fuels were formed. And this is the issue we have today, is that they are running out, and there is no way we have enough time to actually produce them all over again, because the whole process takes millions and millions of years. The issues we have though in terms of burning those fossil fuels, it's all to do with climate change and global warming. So the issues we have when we do complete combustion, when carbon dioxide is released into the air, remember that carbon dioxide is a greenhouse gas, so it contributes to global warming. That rise in temperature causes the ice caps to melt, so you see a rise in sea level, and then due to that you see a flooding of low-lying land, so loss of biodiversity, which means all the vegetation and animals are killed that live on those areas. You see a change in bird migration patterns, because birds will tend to fly across large parts of the world in order to get food, but all this climate change will cause them to not know where they're supposed to be going, and you'll see extreme weather. So all those storms that we were aware of, Jose, Maria, Harvey, I'm trying to think of all the different names of the hurricanes that were this season. This is all due to climate change, so why Trump is denying it is just disgusting. But yeah, climate change is real, guys, and we need to do something about it. Anyway, this video isn't about me banging on about climate change. I'm going to move on now. I'm going to talk about the different types of pollution formed by our various human activities. So I've already mentioned carbon dioxide. I previously mentioned the fact that sulfur impurities in crude oil, nitrogen and oxygen reacting in car engines forms nitrogen oxides, sulfur dioxides. That forms acid rain, which when it falls damages limestone buildings, destroys trees, makes lakes and ponds too acidic. You've got things called particulates, which is like soot particles that come from diesel engines, which cause global dimming. Now we're going to list some examples of resources which are finite, which means that they will run out. So that's your fossil fuels, it's your crude oil, and it's your metal ores, so things we use in iron extraction, aluminium extraction, for example. If we wanted to list some renewable resources, we could talk about the fact that sugarcane and wood, they can both be grown time and time again, as long as we have the space to grow those plants. Next topic, sewage treatment. Lovely. So first of all, what are the steps involved in water purification? You can write loads on this, but I want to make sure you're learning as least as possible for the most marks possible. So simply, all you have to do is filter to remove solids, and secondly, you need to add chlorine to kill bacteria, and we know that that is a super essential step. If they ask you what desalination is, it means the removal of salt from the water. Oh, another really bizarre bit, which is describing the process of reverse osmosis in water purification. Remember that membranes are needed to separate the dissolved salts from the salty water, and secondly, remember that high temperatures are needed, so it's a very high energy cost process. Faces! Lyra! So to this end, what is the disadvantage of using distillation to purify water? Kitten! Oh my goodness, twice in one video! So cute! So kitten, what is the disadvantage of using distillation to purify water? Well, it needs lots and lots of energy, doesn't it? Which means it's a very expensive process. Kitten. Kitten, are you really muddy? No, you're quite... Hey there. Help everyone with their chemistry. Okay, bye. So if they ask you about sewage treatment, the three main steps, it's very similar to water purification. So you need to filter to remove solids, you need to add bacteria to actually feed on the sewage, and you need to carry out sedimentation, which is actually the process which makes sewage sludge. It's hard to say sewage. I think I'm saying it wrong, more and more wrong the more I say it. Going on to the extraction of metals, I've already looked at the extraction of aluminium using electrolysis, but now we're going to look at the extraction of copper. Remember, it's a very useful metal. It's used for lots of our wiring because it's a very good conductor. Two main ways then. Number one, smelting, which means roasting that copper ore with oxygen at very high temperatures. The second way is more complicated. It is using electrolysis, and what we do is we add sulfuric acid in order to make copper sulfate solution, which we can then electrolyze to obtain the copper. However, more and more, increasingly, we're finding that copper reserves are running out, so we're turning to other methods to actually obtain our copper. One of those methods is called bioleaching, the other one is called phytomining. This is very useful where there's very low grade copper, and what that means, it means poor quality copper. It means soils that contain very small amounts. But what happens is in bioleaching, the bacteria feed on that copper, and in phytomining, the plants absorb the copper ions in their roots, And then what you can do is that you burn those plants, and then with the ash you dissolve that in sulfuric acid and then carry out electrolysis on it. More about the environment then. What does LCA stand for? Life Cycle Assessment. I've never taught this in my life and I've been teaching this for a while. What is the purpose of LCA? To look at the environmental impact of products, services and processes. So what are the main steps involved in LCA? I suppose it does make sense. It's raw material extraction, manufacture, the use, reuse or maintenance of a substance, and recycling and waste management. Whew. I could not ever be bothered to learn that. That is just so extra. I like the next bit because we're back to talking about metals. This time we're talking about the rusting of iron. So remember, rusting is about metals breaking apart, lots of flakes falling off, them losing their structural integrity. Now just so you know, rusting only refers to iron. Zinc can't rust, neither can titanium. So yeah, rusting applies to iron. What conditions are needed for rusting to occur? You very much need two conditions. You need oxygen and you need water. Now there are lots of ways in which we can help prevent rusting from occurring. There are the cheaper ways like painting or adding oil or grease to something like a bicycle chain, and that provides a barrier method, so it actually prevents the water getting in. If you're feeling fancy, you can do something called galvanizing, which is when you cover the iron with a more reactive metal, so it tends to be zinc. And this is called sacrificial protection, because what will happen is the zinc, being more reactive, will react away before the iron, meaning that the iron can never actually rust. 3. Figure 2 shows 4 test tubes a student set up to investigate the rusting of iron. This is the method used for each test tube. Measure the mass of nail using a balance. Leave the nail in the test tube for 6 days. Measure the mass of the nail after 6 days. And we've got lots of different experiments. Now, even before, because, I mean, it depends how quick you are, but even before I look at the question, I like to get an idea of what it's about. So because we're looking at rusting of nails, remember the conditions needed for rust is you need oxygen and you need water. So bear those in mind when you're going to work out how much they've rusted. So test tube 1, iron nail, water, well, it's exposed to the air, which means there's oxygen in it, so we're going to expect rusting there. Test tube 2, they've sealed it with a rubber bung and the air is dry, so effectively there's no water there, so no rusting can occur here. Test tube 3, well, we've got plenty of water, but the oil is preventing oxygen reaching the iron nail, so I wouldn't expect any rusting there. They've painted the iron nail in test tube 4, and paint is always a good barrier method against rusting, so we're going to say no rusting there. We've got a painted iron nail, but unfortunately we've got a scratch, which means that there's an exposed bit of the iron nail. We've got lots of access to water and also oxygen, so I'm expecting rusting there. Galvanized iron nail and a scratch. The beautiful thing about galvanizing is it doesn't actually matter if there's a scratch, because the way in which the chemistry works means that it can't actually rust, so I wouldn't expect any rusting there. And that would literally, I mean, it would only take me about a minute to work that out, so it's up to you guys if you're going to spend that time doing that beforehand, but it does mean that when you get to the next questions, hopefully you're a bit more prepared. Table 2 shows the students' measurements. So we're looking at the mass of the nail before and then the mass of the nail afterwards. So when it hasn't rusted, you'd expect the mass to stay the same. When it's rusted, you'd expect it to increase in mass due to the addition of rust. And as we scroll down, yeah, we can see that there's been rusting on the first nail and the 5th nail, which if I look back, yeah, that's what I anticipated when I was doing my working out before, so that's good. What is the resolution of the balance the student used? So you're having a look, it's to 2 decimal places, which means that the answer here is 1 times 10 to the minus 2 grams, the second option. Calculate the difference in percentage increase in mass after 6 days of the nail in test tube 1 and the nail in test tube 5. Make sure you give your answer to 3 sig fig. So percentage increase in nail 1, you're looking for the change, so work out the difference in those 2 numbers, pop it over the original and then times it by 100, and then you want to work that out, which would be 5.44. Percentage increase in nail 5, again work out the difference between the 2 numbers, 0.08 over the original mass times by 100, which gives you 0.8537, and then work out the difference between those two numbers and make sure you put it to 3 significant figures, so final answer is 4.59. Use the results of the students' investigations to draw conclusions about the factors affecting the rusting of iron. Include an evaluation of the effectiveness of different coatings at preventing the rusting of iron. 6 marks. Okay, I love this question because I effectively did all the working out at the beginning when I was chatting through all the various diagrams. So first of all, state which nails rusted. So you're going to say the nail rusted in tubes 1 and 5. The nail did not rust in tubes 2, 3 and 4. And then just make a few more comments. You could say things like the test tube 2, there was no water present. In test tube 3, there was no oxygen present. Test tube 4, the paint stopped the rusting. Test tube 6, the scratched galvanised iron did not rust, and that's because galvanising stopped the rusting. And therefore the conclusions we can draw is that both water and oxygen are required for rusting, that various coatings have different levels of effectiveness at preventing rusting. So although paint, when perfect, prevents rusting, when it's scratched, rusting occurs, whereas with galvanising, there's a scratch and rusting still doesn't occur. So we tend to think that galvanising is better at resisting rust than paint. And then you could actually have a little chat about what galvanising is. Remember, it's all to do with sacrificial protection. So when you coat the iron in a more reactive element, zinc, and what happens is that corrodes preferentially, meaning that the iron can't rust. So yeah, I really do like that question. Rust is hydrated iron 3 oxide. Complete the word equation for the reaction. So it's the word equation. So we just need iron plus water plus oxygen forms hydrated iron 3 oxide. Already mentioned it, but I'm going to mention it again. What is an alloy? It's a mixture of 2 or more metals. Why are alloys harder than pure metals? Because they have ions of different sizes. The layers are distorted, which means the layers can't slide over each other, and therefore it's a much stronger substance. What is stainless steel? Well, it's an alloy made up of chromium and nickel, as well as obviously steel. Lyra, what are you doing? So what are the useful properties of stainless steel? Why do we do it? Well, because it's very hard, it resists corrosion, it's very strong, and we can make use of these properties in using stainless steel to make cutlery. Lots of cutlery is made up of stainless steel. Check it out next time you're eating. Next up, we're looking at glass. So how is glass made? By heating a mixture of sand, limestone and sodium carbonate. They want you to know how borosilicate glass is made. I have no clue what this is, but apparently you need sand and boron trioxide, and this produces glass with a higher melting point. So what is a composite material? It's a substance made up of 2 or more materials which give good properties. This is how you do balancing equations. I always do it the same way. So draw a line separating both sides of the equation and then list the elements. So we've got hydrogen, chlorine, zinc, carbon and oxygen, and then just copy it across exactly as you've done it. Keep them all lined up, that's crucial. And then you're going to use the tally chart to work out how many atoms you have of each element. So we've got 1 hydrogen, 1 chlorine, 1 zinc, 1 carbon and 3 oxygens. Let's do the same for this side. Hydrogen's 2, chlorine 2, zinc 1, you've got 1 carbon and you've got 3 oxygens. And now it's just a matter of comparing them. Okay, well we don't have enough hydrogen and chlorine on this side, so you'll put a 2 here. Remember, you have to add a big number at the front. That's the only thing you're allowed to do when balancing equations. Make an adjustment because we now have 2 hydrogens, 2 chlorines. Step back, and yes, you can see they're all balanced, so that is done. Here's another example. So line down the middle, list your elements, iron, oxygen and hydrogen, copy them across, and then tally chart. We've got 1 iron, the 3 applies to everything inside the brackets, so that's 3 oxygens, 3 hydrogens, 2 irons, 3 plus 4, so that's 4 oxygens, and then 2 hydrogens. The obvious thing here to do is match up those ions first of all, so we're going to put a 2 there, adjust, and the 2 applies to everything. So you now have 6 oxygens, and you have 6 hydrogens. And then we don't have enough on this side, so I'm going to pick a sensible number, which would be 3 here, because it means that I now have 6 hydrogens. And then readjust your oxygen, so you've got 3 oxygens plus 3, so that's 6. And yay, both sides match, so that's how you do the more tricky ones. I'm just going to show you how to work out the formula of common compounds. I'm going to show you the quickest, easiest way. and it is called swap and drop. So you'll be asked for something like work out the formula of aluminium oxide, but obviously you don't know because that's the final answer there. So what you do is you grab the ion for aluminium, the ion for oxygen, and then you swap and drop, which means you take the 3 from aluminium and drop it down to oxygen, and you take the 2 and drop it down to aluminium, so your final formula is Al2O3. The reason why that works is because you have on both sides 6 plus and 6 minus charge, which means they balance out. Check out my common ions video if you're not following. But just remember, those little numbers must go at the bottom. We take the second example, calcium chloride, we swap them over, so the 2 lends itself to chlorine down here. The 1, which, because although you can't see the 1, that's what that minus means. It means it's 1 minus. You take that down to here, and because it's 1, you don't need to write it. So the final answer here is calcium chloride, CaCl2. Slightly more tricky example here, which is ammonium sulfate. You're taking the 2 down from sulfate and dropping it here. You've got the 1 at the top for ammonium and taking it down to here. Now, luckily, that's actually all you have to do. Don't get freaked out when it looks confusing, because I promise it's simple as long as you follow these rules.
Oh, I think we're nearly there. We're going to talk about the Haber process now. So what is the point of the Haber process? Well, it's to make ammonia. What raw materials are needed in this process? Well, you need hydrogen, which comes from natural gas, and you need nitrogen, which comes from the air. Remember the equation for manufacturing ammonia? I'm going to add that now, but you're mixing hydrogen with nitrogen to produce ammonia. It's a reversible reaction, which is a bit of a nightmare because it means we don't get 100% yield. We get some of our products lost. And so remember, we choose very specific reaction conditions in order to maximize our yield. Now, remember, we need to know the words exothermic and endothermic because this is very strongly related to this topic. So exothermic means that heat energy is given out, so you feel it getting hot. Endothermic means that heat energy is taken in, so you feel it getting cold. So in terms of working out which reaction conditions will work out best, you need to look at the forward reaction in terms of the ammonia production, and we can see that it's an exothermic reaction, which means it gets hot. Now remember, with reversible reactions, whatever you do to the reaction, it will try to oppose that change. So if it's getting hot, you want to encourage that by making it get cold so it tries to get hot again. So you choose a low temperature because a low temperature favours an exothermic reaction. If you're not following what I'm saying, check out my Haber process video, which is separate to this. If you still don't get it, just learn the summary I'll add at the end of this chunk because I promise you'll still get full marks. So yeah, you want to choose a low temperature because the forward reaction is exothermic. However, low temperatures result in low rates of reaction because quite simply the reactants don't have enough energy to come together very often, they're just drifting. So you actually have to increase that temperature in order to cause them to come together. So in terms of the temperature chosen, it's not low at all, it's 450 degrees Celsius. Now we'll look at the pressure. In order to work out which pressure will favour the ammonia production, you need to count the number of moles of gas. So if you look at the number of moles of gas on both sides of the equation, you can see that there are 2 on the right hand side, 3 on the left hand side. So in order to favour that right hand side, you want a really high pressure. And that actually also favours kinetic energy. So both rates of reaction and yield will be high if you use high pressures. However, high pressures are dangerous and very expensive. So we'll tend to use a lower pressure for that reason, and we use a pressure of 200 atmospheres. Because it's such a bad reaction, they'll also add an ion catalyst, but remember, that doesn't affect the yield of ammonia, it just increases both the rates of the reverse and forward reaction. What is the whole point of this process? Well, it's to produce ammonia, which can be used in fertilizers. Name one of these fertilizers. That's NPK, N standing for nitrogen, P standing for phosphates, and K standing for potassiums. I'm done! Yay! Oh my god, I'm so happy! Yes! Let me know, guys, in the comments below if you actually got this far with me. Oh, wow. Yes, I'm so happy. All I have to do now is edit the damn thing. Great. Anyway, hope the cat will keep me company with that. Hope your revision's going well. Please, please like this video if you liked it because they are an absolute killer to make. I can't explain how long they take me. So if you'd like to see a similar video for biology or physics, you must let me know with likes. Don't forget to sub and tell your friends about my channel. And come follow me on Instagram and Snapchat because I've got lots of extra tips available there. See you, bye!